All right, that's the reason iCloud's a horrible idea, especially for those of you that have kids. Your stuff gets mixed in with, well, actually, I should say their stuff gets mixed in with your stuff, and that's what you end up with on your iPod. Guys, in multiple regression, we often, I was going to complete the sentence, but I just had to get rid of that. In multiple regression, we often are interested in removing more than one predictor. And for example, let's say that we have a full model, which is a 3 predictor model. And we would like to see about removing x2 and x3 to come up with a reduced model, which obviously will be this model. Okay, now a situation where you may be interested in something like this. It typically seems to happen out there in the real world when x2 and x2 and x3 are variables that are harder to get your hands on. Let's say, for example, that we are an admissions director at some university, and we're trying to come up with a criterion by which we let people into our university. So let's play even a little bit further that we are an admissions director at a highly selective university who have more people applying than we have slots to accept. So let's say that Y is we have some sort of accept index. And this thing runs from 0, no way are we accepting the person, to 100, give away the house. And obviously I'm being facetious here. Give away the house just means give them a full ride, get these people in our university. Some things that we probably would take a look at, and again, since this is a fictional situation, fictional case, let's say that the admissions director has looked at other research at other similar highly prestigious universities, and let's say that the ACT or SAT, typically universities don't require both, but let's say whichever one is accepted. Or preferred. And let's say x2 is something else that's pretty easy to get a hold of, and let's say that's the high school GPA. But let's say previous research shows that this dispositional scale that's been created to, it's a questionnaire that you can give people, potential students, prospective students, that taps into their, those dispositional data. How motivated are you, and on and on. And then there's an additional scale that the admissions director has called a situational scale. And guys, just for an FYI, situational and dispositional data have been shown to be extremely predictive of course success. And, obviously, pretty much, if you're going to be successful in your courses, there's a pretty good chance you're going to be successful in completing your degree. Not always, but not bad. Well, as you can see what I'm setting up here, ACT and SAT are submitted. Those scores are easy to get. Part of the application package is typically your high school transcripts, so your high school GPA is easy to get. But these, X3s and X4s, this dispositional data and situational data, those are tougher. They take more extensive testing, and it gets into validity and reliability and things of that nature. But you would probably use a pre-existing test to develop those. So the admissions director would like to know if he or she can eliminate these. So there's a model that's been used at other universities, and the admissions director is trying to obviously create one at his or her university with easier to get data, ACT and high school GPA. So guys, let's if we wanted to drop, let's assume we'd like to drop that's a 3, by the way, beta 2 and beta 3 from our model. So we'll check, or we'll test the alternative. Kind of as I would hope you would expect. Against equals 0. Okay. So again, keep in mind that the reduced model here is ultimately what we're testing. And actually, that would be the alternative, right? Because if we get statistical significance, that means that we will drop the models, or drop the beta 2 and beta 3, and so this ultimately would be testing. All right, let's remember a couple things. First of all, the sum of squares for the regression in the reduced model would just be equal to the sum of squares. Oh no, guys, I'm thinking correctly, but I wrote it incorrectly. So the sum of squares for the reduced model, sum of square. Oh wow, sum of squares error for the reduced model is just sum of squares for x1 for obvious reasons, because the reduced model only has x1 as a predictor. And guys, we should know that the degrees of freedom for the reduced model would just be n minus 2 because the only things that we're predicting in the model would be beta 0 and beta 1. So guys, the F statistic, which you should know a little bit about by now, hopefully. Okay. Some things I know is the degrees of freedom for the denominator is going to be n minus 4. And down here we're going to have the sum of squares error of the full-on model. And degrees of freedom would be n minus 2 minus n minus 4. And sum of squares for the error will be x1 minus the sum of squares for the error for the full model. Well, that got kind of crazy. Okay. So remember, when we're looking at sum of squares error, the error is going to be the biggest when you have the least terms in, and then as the number of terms increases, your error will either stay the same or decrease. Now, okay, I want to focus on this part right here. So we should know that the sum of squares for the error of x1 minus the sum of squares 1, x2, and x3 is nothing more than the sum of squares for the regression of x2, x3 added to the model when x1 is in the model. And we saw that earlier. No, actually we've seen that in I think every video so far except for one. And you know, this is one of those things that you just need to tattoo to the brain, if you will. So guys, that leads us to I'll tell you what, let's get a full sheet here. That leads us to f star equal degrees of freedom 2 and degrees of freedom n minus 2. And let me make sure I'm not doing something crazy here. Minus 2 plus 4, yeah. And then, of course, we're going to have sum squares regression for adding, yeah, to x3 to the model. When x1 is in our model, and then down here we've got sum of squares for the error for the full model, okay? Now, what I would like to do is, I think the last time I demonstrated we used high school GPA and or something like that. I forget exactly, but I want to go back to the body fat example, and let's if I remember correctly, and I'm pretty sure I do here, y was body fat. And the predictors were some sort of skin fold tricep measure, which I'm just going to call tricep. And it seems like x2 was some sort of thigh measure. And x3 was like a mid-arm circumference or something like that. So let's say that all of this collectively, we will call this our full model. But we would like to come in and see if we can drop the thigh and mid-arm from our model. And of course, we're going to call this our reduced model. And you're going to see with R, it's going to be very, very, very simple to carry this out. So let me, speaking of R, let's get out of this and get R going. First of all, let me make sure I've got body fat. Yeah, I didn't. I'm shooting from the hip on this body fat thing. All right, so let's do what we need to do. I have no idea. I took down some notes, and I was going to use the ACT data set, and I just decided midterm to, or midstream, I should say, to change. All right, so we need to attach data, and I want to also look at the names of data. Okay, so I've attached it, and the names, so I'll know how to type stuff in. All right, gang. The first thing I want to do is I want to look at the numerator of the numerator. Okay, so the numerator of the numerator looks at the addition of x2, x3 when x1 is already in the model. So probably the easiest way to do this is to oh, I don't know. Let's just call it model 1. And we're going to take the linear model and we're going to predict body fat from triceps. So from here I can do summary of model 1. And it doesn't give me what I want. I need ANOVA of model 1. Alright gang, so the sum squares regression for just x1 in the model is 352.27. Now what I want to do in model 2 is I want to look at body fat, but I want to look at triceps, and I want to look at what's it call it, thigh and mid-arm. All right, and even though I don't want summary, I want to illustrate something here in just a second where I'm going to need this. And then I want to look at ANOVA model 2. All right, gang. If you look at triceps, 352.27. I like the way that R does this. We can see that the addition to the sum of squares for the regression is just the sum of 33.17 and 11.55. So we can do that in our head, and that's what, 44.72. So I'm going to write that down, and we'll come back and get that in just a second. Our degrees of freedom clearly on the numerator are going to be 2. And the next thing we need to do is we need to look at the sum of squares for the error for the full-on model, and that's what we have right here. So that's going to be 98.40. And then the degrees of freedom for the denominator, just n minus 4. Because in the full model we have beta 0, beta 1, beta 2, beta 3 that we've estimated. So we have to subtract 4 from n to account for that. All right, so guys, that's really pretty easy, pretty cool. So when we go back here, this value right here is 44.72 divided by 2, and this value right here turned out to be 98.40. So let me get my calculator. That's going to be 22.36. And 98.40 divided by 16. Let me go ahead and put this in here too. All right, so 98.40 divided by 16 gives us 6.15. So gang, we got 22.36 divided by 6.15. It looks like we have 3.64 as our test statistic. And our degrees of freedom are 2 and 16. So I know you've seen this ad nauseum, but I'm an ad nauseum kind of guy. So we're better hurry up. I just got a low battery warning. So we're looking at a model F distribution degrees of freedom 216. and we're looking to the right, I think 3.64, yeah, 3.64. So guys, let's go to R and see what our p-value is. So guys, I would hope that we know by now that we're going to do 3.64 comma 2 comma 16. And wow, that's close. Okay, so our p-value is 0.04978. I don't know about you, but I call that one a wash. And it is statistically significant. There's no questioning that. Barely. So when we go back to our the null that we're testing, versus at least one of these is not equal to 0. We're going to reject that, not strong, and conclude that we can remove B2 and B3 from the model barely. Okay. Now, when we just a little bit of FYI here. When we're testing just one, the removal of just one beta, then we can test this one of two ways. We can test it using the F statistic, or we can test it using the T statistic. And of course the relationship here is that the t-square value will be equal to the F value using the appropriate degrees of freedom. Well, this isn't true. Well, it's not so when we are testing the removal of more than one predictor. But there is another way that we can do this. There is something called a multiple R squared. And if you go back to R, you're going to see that, well, you're going to see the reason I did this. If you go back to R and look at where I did summary of model, now don't get confused with the adjusted R squared, but if you come down to the multiple R squared, you get exactly what I'm talking about. Well, it turns out that there is a test statistic that, let me get back to the blackboard here. There's a test statistic, an F star, of this form. So it turns out that this is, well, I'll tell you what, let me go ahead and just do the full on here. So the numerator of the numerator is just the multiple R squared for the full model minus the multiple R squared for the reduced model, and then take the degrees of freedom for the full model minus the degrees of freedom for the, let me be consistent here, for the reduced model. This is divided by 1 minus R squared for the full model, and then of course the degrees of freedom for the full model. Now, we know that for our problem, this is going to be 16, and this is going to be 14. So the degrees of freedom for the numerator will be equal to 2. And degrees of freedom down here, of course, will be 16. So really all we got to do is we got to come in and find the multiple r squared for the full and the reduced model. And R does that for us quickly. So guys, this only included, so model 1 just included triceps, so the multiple r squared of 0.7111 would be for the reduced model. And model 2 was the multiple r squared, so we got 0.8014. And so guys, on the numerator of the numerator, we get 0.0903. Over 2. And we get 1 minus 0.8014, so 0.1986. And that better turn out to be 3.64 or 63 or whatever it was. Or I'm going to look like an idiot. What's new, right? And we get 3.64, just as we should. Degrees of freedom, are the same, so there's no reason to think we don't get the same p-value. All right. Now let's go on to. You know what? Let's call this one. Let's take this slower. I don't want to do that other stuff just yet. We'll put that in the next video because it's gonna. As I'm sitting here looking at my outline of what I'm supposed to be doing, it's gonna take more than the time that I have available. So guys, that's the end of the video. Have a good one, and I promise I won't play wobble anymore. Okay, take care.